I don't know what analogy we have for this, but maybe going down a long corridor that has doorways in it. Each doorway is like a resistance. You have to stop, get out your key, unlock it, go through the door, right? You walk down the hallway some more, you hit the second door. You got to stop, get out a key, unlock it, go through it, right? You go down, you hit a third door. You might as well have stopped with one door with 3 locks in it and gotten out your first key and unlocked the first lock and your second key, stood there and opened it, then gone through the one door, right? It's equivalent. One big resistor versus the individual resistors. So when they're in series like this, we just add up the effects. Okay, when they're in parallel, and remember, series, maybe I should give you a definition of series so we know for certain. Series means the current through each resistor is the same. Okay, the current through each resistor is the same. You see that? Because there are no junctions. There are no forks in the road. All the current that comes out of the battery, it has no choice. It has to go through the first resistor, the second, the third, and then back to the negative terminal of our battery. It has no choice. Okay, so the current through each one of those is going to be the same. They are in series. In parallel, we usually draw it like this. So we got an idea from looking at the 2 light bulbs in parallel. And we had one flowing. We knew it had a certain current I1 in it. We added a second one in parallel. And the 2 light bulbs each had current I1. So the total current in the circuit increased. Which meant if V stayed the same, because we now know what Ohm's law is, if V stayed the same, and I increased, then the resistance had to go down in that circuit. There was less resistance. And we said it's like at the supermarket, the checkout, right, is like a resistor, right? You've got to stop, they check everything out. Hopefully there's not an old lady in front of you with their checkbook out, buying 100 cans of cat food. Slows you down, right? You have to decide which path you're going to take. So the current is doing the same thing. And if those R's are all the same, then the same amount of current takes every path. But those R's might be different, right? Sometimes you get to the checkout, you got the person getting their checkbook out in front of you, and sometimes you've got the quick check lane. You got to decide which one to go. So you run over to the quick check lane, right? You want the easiest way out. But what if there are already 10 people in the quick check lane? There's only one person in front of you, but it's the 100 cans of cat food and the checkbook out. You've got to decide, right? You've got to make a decision. What's going to get you out faster? The big resistance, right? The person with all the cans, the checkbook, right? A big resistance, going to take them a long time to check out. But there's only one person there. This is a small resistance. It's the express lane, right? But there's already a bunch of people there. So maybe you go here. You decide. You have to decide which is going to get you the quickest way out. So when there's some resistance in every path, the current splits. The most current takes the path of the smallest resistance, but some current takes every path, because as long as there's some resistance in every path, it's sort of like, the supermarket, right? You might decide that it's quicker to get out going behind the person with the overflowing cart, because there are a bunch of electrons already lined up in front of you at the smaller resistance. Some current takes every path. More current takes the path of least resistance. Less current takes the path of more resistance. It splits up. If the resistors are all the same amount of current takes every path. Somebody asked earlier, what happens if there's a zero resistance path in there? What happens if you just hook up a wire? This is sort of a side note here. And we have I coming out here. How much is going to go through those? I need my... no, wrong side. Hold on. Okay, so what I've got here, the electricity comes along here, it goes through this wire, and it has a choice here. It can go through the light bulb and through this light bulb, or it can go around when I connect this. So this is what I have. Let me draw it. I have a battery, and I have a light bulb here with a switch, and then I have another light bulb. So what I'm doing when I close that switch, I'm creating a zero resistance path around that light bulb. So we want to know what's going to happen to this light bulb. You ready? Let's see what happens. Take this away. I guess we don't really care what happens to this one, right? What happens to this bulb? We connect a zero resistance path across it. And we said when every path, the path through the light bulb, the path here, when every path has resistance, some current takes every path. More takes the path of least resistance. But the exception is when there's a zero resistance path, all the current takes the path of zero resistance. Okay? When there's a zero resistance path, all the current takes the path of zero resistance. And my hand gets a little bit brighter. So when we close this, what happens is the I through here is 0. And if this is I1, then we get I1 flowing here and I1 flowing here. Okay? Nothing goes through that resistor if there's a zero resistance path for it to go. We call that, what do we call that? Nobody does electronics. A short. We call that a short. Short circuit.